Before I start, let me introduce you to my team of brilliant collaborators. This is Bjorn Brinkman, who is at the Institute for Advanced Study at Princeton, Yu Deng, who is at the University of Southern California, and Haitian Yue, who was my PhD student, and after spending some time at USC, moved to Shanghai Tech and is here with us today. There it is. Okay. And I owe a lot to the three of them who helped me with this presentation. And so everything nice that you will see is due to them, and the rest is just me. All right. So let me start talking about, so I'm a mathematician, so this talk is about mathematics. Okay. So no pictures of the universe. And this talk is about essentially how analysis, probability, PDE, and some tools from analytic number theory, combinatorics, and geometry actually helped answer questions that were posed and motivated in equilibrium statistical mechanics and constructive quantum field theory about sort of probability measures for certain physical systems, which are called Gibbs measures. And many of the tools and techniques that we use here to answer the questions that were posed here also have a bearing or related to questions in turbulence theory, but we are not going to talk about this today. So let's start with something easy, which is ODE systems. So suppose you have a physical system, and here what I want you to think of is something like a spring mass system with a nonlinear forcing acting on it. And so you're giving a potential energy with nonlinear interactions, and there's two ways you can go, right? From there, once you have that, you can write a Hamiltonian ODE. Or if you have sort of a random forces or fluctuations, you can write some form of some type of Langevin stochastic differential equation. And both of them, it doesn't matter which way you go, both of them give rise to essentially the same Gibbs measure. And so let me illustrate this for you. And let's start with, for example, an example here of a potential, which is sort of a q squared over 2 plus q to the 4 over 4. So if in the spring mass system, q would be the displacement from equilibrium. So this is a position as a function of time. And p is the velocity, so it's the derivative respect of time of q, or momentum. So you have your Hamiltonian, which is sort of p squared over 2 plus the potential. And the Hamiltonian ODE, which is written here, is simply dt, or q dot p dot equals dp h minus dqh, which is simply p, and then for the second equation you have minus q cubed, which is equivalent to this second order equation, which is what you will get if you use Newton's second law. Right? So what is the Gibbs measure? So the Gibbs measure is then defined for this system as the exponential of minus, so beta here is a parameter, is a constant, and it will play no role in my talk. Usually from questions in statistical mechanics and so on, this is kind of like 1 over the temperature. But I am not going to ask anything about beta, so beta will be 1, okay? And if you see a beta, it's just 1. So it's fixed. So it's just the exponential of minus the Hamiltonian times the Lebesgue measure. And this z here is just like a normalization constant so that you have a well-defined probability measure, okay? So in the example for the potential that I gave you, then this translates into simply exponential of minus q to the 4 over 4 times, I put the q squared here, times a Gaussian measure, okay? So this Gibbs measure is nothing but a weighted, this is the way, this is like the Radon-Nikodym derivative, it's a weighted Gaussian measure. And so it's absolutely continuous with respect to the Gaussian in the sense that the measure of a set of a Borel set is 0 every time that the measure of the raw measure is 0. And this is actually a property which we will see at the end of the talk that it actually can fail in infinite dimensional setting. So this measure is actually invariant under the Hamiltonian flow, which I call phi of t, which it just means that if you take an initial ball and you flow this ball under the Hamiltonian flow, then the measure, the measure of the initial ball and the measure of the flow ball is the same. Okay, and why is this true? Well, this follows from the fact that the Hamiltonian is a conserved quantity of time, so it's the same at time equals to 0 or at a later time. And you also have Liouville theorem for divergence-free vector fields, Hamiltonian is divergence-free, that tells you that the Lebesgue measure is volume-preserving under the Hamiltonian flow. So you taking these two facts into account, that follows easily that you have this invariance for this measure. Okay. So let's go the other route. So suppose that instead I give you the same potential. So here now I put a drift term, minus v prime q dt, plus time-wide noise. B here is Brownian motion. So minus v prime is a 1D gradient flow, so it's sort of making the potential energy decrease. And so the noise is here to kick in the energy back into the system, okay? So that the energy is sort of conserved in some sense. And this plot is due to Bjorn, and actually is a plot of what the solution would look like. And anyway, so the measure here will be defined as d nu of q being the exponential of minus v, the Lebesgue measure with the normalization. And this measure is also invariant under the dynamics of this overdamped Langevin stochastic differential equation. And to see that is a little bit more complicated, but essentially follows from Ito calculus. Okay? And actually, what you should note is that these two measures are essentially the same measure. I mean, they differ simply on a Gaussian measure, which is exponential of p squared over 2. And so if you understand one, you understand the other one. Okay? So that's what I meant at the very beginning. So we are interested not in ODEs, but we are interested in PDEs. And so what is the picture or the analog of what I just said in PDEs? So now we are going to be given a field or a function. My underlying space in this talk is always a periodic box in space. So I have a function that goes from the d-dimensional torus, and it could be either real or complex value. And then your energy is going to be defined by the integral over the torus of phi squared over 2, gradient of phi over 2, plus, and now instead of taking power 4, I'm going to take, instead of taking like sort of four-wave interactions, I'm going to take p plus 1 wave interaction. So p plus 1 is always even here. And so this is more general. So in the previous examples, p plus 1 was 4, p is 3. And so formally now, we can also associate to this energy a Gibbs measure. And I say formally because here you have kind of like an infinite dimensional Lebesgue measure, which is total nonsense. And so that measure will look like that. And the point is that there is three different dynamics that you can actually associate to the same measure, which are called these p plus 1D models, which is a stochastic nonlinear heat equation, which is the analog of the Langevin situation, a nonlinear wave equation, which would be like a Hamiltonian, real value Hamiltonian, or an NLS, which is the complex value Hamiltonian, a complex value situation of the Hamiltonian. And so what is it that we're interested here? So there's two questions. One is, when is that this measure can be formally, not formally, rigorously defined? And then we are interested in sort of the dynamics of this measure, meaning we are interested in understanding when is this measure invariant under the given flow. And that question comes together with the question of having global strong solutions on the statistical ensemble of the measure. Okay? So for the same measure, we could take these three different dynamics. And so let's try to see what was known, what is known. I mean, this subject has more than 60 years. And so it's very hard to review the whole literature, but let's try to get a slice of it, a little bit of it. So in the first column here, I have the dimension. In the second column is the measure. The third, fourth, and fifth columns are about the dynamics. So here is about the construction of the measure. This is about the dynamics, meaning the invariance of the measure under the corresponding flow and the existence of global strong solutions in the statistical ensemble of the measure for these equations. So what is it that was known? Well, dimension 1, the construction nobody knows really who is due to, but we can give it to Nelson in 1966. And the construction of the measure in dimensions 1 and 2 can be done for any p odd. Okay? For any p bigger or equal than 3, you can construct a measure in dimensions 1 and 2. Okay? And this goes back to the mid-60s. And perhaps one of the most celebrated results from quantum field theory came from in the mid-70s from the work of Glimm and Jaffe, who proved that in dimension 3, you can only define the model when p plus 1 is 4. So when d is 3, the only power that works is p plus 1 equals to 4. So this is the well-known phi-4 model, and that's the only one that exists in dimension 3. And then there is work from the 80s from Einsmann and Fröhlich that actually they prove that in dimensions bigger or equal than 5, you have what is called the marginal triviality, which essentially means that no matter how you try to define this measure, okay, how you approximate it, how you discretize, how you renormalize the potential, whatever you do, in the limit you will always get a trivial measure, which means that you will always get a Gaussian measure. So it cannot, there's nothing there. And very recently, actually, and this was mentioned in the Fields medal of, sorry. Okay, no, let me go back. Let me continue. So then, in dimension 1, so the dynamical questions for the heat and the wave are due to Iwata and Freelander. Okay, and this works for every p. Remember, this is every p odd, p plus 1 even. And then we have, later on, in the 90s, the work of Bourgain, 1D for every p. Okay, this is very hard to use. This is 94. Then in 96, he proved that the 2D Schrodinger equation, you have a measure, but only when p is 3, but the measure exists for any p. But he only could prove it for p equals to 3. That was actually a huge breakthrough. This result is a huge breakthrough with respect to this one. And then he also proved it for any p in the wave equation in 99. Okay? And then what happened was that also in the heat world, in the diffusion world, D'Aprato de Bush in 2003 also proved that you have the invariance and the existence of global strong solutions for any p on the stochastic heat equation. Okay? And essentially, nothing happened for a long time. Okay? Until actually the breakthrough of Martin Hare that came in 2013, 2014, who actually developing the theory of regularity structures, he was able to answer the questions about the dynamics and the invariance for the stochastic heat equation for the phi-4-3 model under the dynamics of the heat equation. Okay? And this is actually one of the main reasons why he got the Fields medal. Right? And after that, essentially, what happened was just recently, in 2019, in which the question of the existence of the measure in dimension 4 was open. But Einsmann and Duminel-Coupin in 2019 proved again that the phi-4-4, in dimension 4, the measure is also trivial, same as in dimensions bigger or equal than 5. So there is no phi-4-4 measure. It's just the Gaussian. And again, here you have two Field medalists, and this work was also mentioned in the laudation. So this is the state of affairs all the way up to 2019. Okay, so we went from 1960 to 2019. And as you can see in this table, the measure is totally well understood. Everybody understands when the measure can be constructed. So this is very well understood now. For the heat equation, the dynamics are very well understood also. But in the context of dispersive or wave equations, there are holes, right? In 2 dimensions, we don't know what happens for p's that are not 3. So the nonlinear Schrodinger equation when the nonlinearity is not cubic. We don't know what happens with the 4-3 model under the dynamics, the 3-dimensional cubic endless, and we don't know what happens in the case of the wave equations. So these problems are open. Okay, so let me focus on them, because this is a talk, or this series of lectures is about waves, and so we want to focus about these problems. Okay, so if you see in this table, essentially since the work of Bourgain, these 3 problems, which are the only problems open, are open as of 2019. So this is our focus today. So before I go any further, let's just make sure that everybody's with me about what I mean by dispersion. And so what is dispersion? So dispersion means that just when no boundary is present, waves of different wavelengths travel at different phase speeds. So long wavelengths or components propagate faster than short ones, right? So this dispersion is what causes the white light to sort of like a spread in this full spectrum of wavelength, right? That's I think this is a real picture from some Alaska National Park. I don't know. And so this is also the reason why dispersive waves spread out in space as they evolve in time while conserving some form of energy. So I want to contrast dispersive wave phenomena with transport phenomena, where all frequencies move at the same velocity. And I also want to contrast it with the heat equation, or with dissipative phenomena, in which frequencies gradually taper to zero and do not propagate forever. Okay? So it's very different. And so perhaps the nonlinear Schrödinger equation is the one that plays the most important role, one of the most important ones in the dispersion world. So let me actually, as you know, it's like the NLS is sort of associated with nonlinear optics, water waves, Bose-Einstein condensates, right? And here I wrote the equation, which is just I, the derivative of u with respect of time, plus the spatial Laplacian of u, two derivatives of u. And here you have the p power, so u is a complex, is always complex value, so p minus 1 is even, so every time you see this, you have a u bar being multiplied. And I chose the plus sign here, which means that I'm always talking about the focusing equation, and my underlying space is always this periodic box, okay? And so, for example, like if you look at the Bose-Einstein and you actually look at binary collisions of bosons, then you see the cubic equation. But if you do ternary collisions of bosons, then you see the quinticon. Okay. All right. So when the equation, of course, if I take the right-hand side equals to 0, then that's the linear problem. And for the linear problem, we have an explicit solution, which is given by this semigroup, e to the I t Laplacian u0. u0 is your initial condition or your datum, which on the Fourier side can be written as e to the minus I t k squared times u hat k. And so minus k squared is the dispersion relation. Okay? And actually, the semigroup here, there is a unitary semigroup, preserves the L2 norm. These are the only two function spaces I'm going to refer to, which is L2. This is, sorry, the L2 norm. And the Sobolev norms, HS. Okay, here, this is a Japanese bracket. If you don't know what it is, just think of absolute value, which tells me how many derivatives of u are in L2. Okay, so it measures, so S, whenever you see this S, or whenever I say the word regularity, I mean the value of this S. So if this S is positive and large, it means that I have functions which are very regular and very smooth. And whenever this S is negative, it means that I don't have functions. I have actually distributions that things are very irregular. Okay, so this is a little bit the jargon that I'm going to use. And what I want to emphasize once again is the difference between the heat equation and the Schrödinger equation. So if you take data, right, which is very rough, here you have it, and you apply the heat semigroup, then immediately you see that this data not only regularizes immediately, but also decreases very rapidly, right? So it becomes very smooth immediately and decreases very rapidly. But if you actually apply the Schrödinger semigroup, it stays almost the same. Nothing happens. It does not regularize, and it does not decrease to 0. Okay? So this is the reason. I mean, here, what I wrote here is just that, the heat semigroup gains you immediately two derivatives, so you have instantaneous smoothing. But the Schrödinger equation gains you no regularity, nothing. So this is one of the source of difficulties of why in the picture that I showed you before, in the table that I showed before, the questions for the dynamics of wave equations or Schrodinger equations are so much harder, actually, than for the heat equation. Not that for the heat equation were easy, actually. The achievement of Martin Hare for phi43 was really, really a breakthrough. But you can imagine when you have no regularization, the problem is much, much harder. Okay, so NLS has a very rich structure. You can solve the equation forward or backwards, right? And it has a scaling, which I'll talk in a minute. It has conservation of L2 norm. That means that at time equals to 0 or any time you have the same mass. And as I said before, you have conservation of Hamiltonian. So at time equals to 0 or later, you have it's the same constant. So let me talk a little bit about this deterministic scaling, because this is what I want to emphasize a little bit today, which is that this is a number which is kind of like the critical index, so that if you take, whenever this number is non-negative, if you take functions, if you take data whose regularity is above this number, then you expect solutions to exist. But if you take data whose regularity is below this number, then you expect some form of ill-posedness. You expect things to go bad. And so let me convince you of that with some couple of pictures. So here what you have is U1 is just the linear evolution of some data. Okay, I'm taking sort of, yes, that the data has a regularity 0.6. And U2 would be solving, it's like Picard iteration, you're solving, U2 is the solution of the Schrodinger equation with nonlinearity U1. Okay, so you put U1 in the nonlinearity, so it's the next iteration. And we are looking here at time equals to 1, U1 at different frequencies, n equals to 10, equals 50, n equals 100. And then we see what happens at the second iterations at U2. And we see immediately that for higher frequencies, look at here, look at the scaling here, right? This is like 2 to the 10 minus 3. So really, this is really zoom in. What we see is that for large frequencies, this becomes small very quickly. The amplitude becomes small in L2 very quickly and smooths out. So it's not hard to believe that for large frequencies, if you take all the iterates, U1, U2, U3, this will form a convergence series and will give rise to a valid solution, okay? Because things become very nice. However, if you are below this number, so in this picture, this number C is 0, okay? So if you are below this number, say minus 0.1, and you do the same picture, so similar data, then you see that immediately, and the second iteration for high frequencies, the solution becomes very wild and starts growing. So this will never converge to a valid solution. So if you look at the iterates U1, U2, U3, and so on, you will not get a convergence series. So you expect solutions will not exist even for a short time. So, okay, so this is what happens in sort of the deterministic world. But what I would like to convince you, actually, is that the picture is very different in the sort of like probabilistic world. So in some sense, what I would like to say is that in the previous pictures, like in these ones, right, we are looking at particular dynamical trajectories, right? For any function in HS, we are looking at that particular trajectory. And so I'm not interested in that. I'm interested in looking more at what happens when you draw data from randomly from some sort of a ensemble, from some set. And so why is that injecting randomness will be useful? So first of all, we ask the question of, we want to understand and describe how randomness affects the behavior of solutions. And there are many ways in which randomness enters, right? I mean, this is just two. Okay? One is from the equation, as in stochastic problems, from additive or multiplicative noise. And another way is from random initial data. So you have an equation that is deterministic, but your data is random, so you're injecting the randomness through the data. And this is just two. There is many other, of course, there's many other ways of having randomness in a problem. And so I'm going to focus on the second one. Okay? And so let's actually set up a little bit things. So here you have a canonical data, okay, which I'm going to call U omega. So I didn't write the X. This 0 means time equals to 0, which is nothing like a random variable F omega, which I'm going to write as something with Fourier coefficients, random variables which could be Gaussian or uniformly distributed on the unit circle. I mean, they're nice random variables, divided by sort of k to the alpha. And I want you to remember this alpha is going to be defined as some s plus the dimension over 2. So there is so if I give you an alpha, I have an s. If I give you s, I have an alpha. Okay. So the law of this random distribution, of this random variable, the law of this random variable is formally given by a Gaussian measure which is supported just below HS. So if I put an alpha here, then actually this is actually supported is with probability 0. F omega is with probability 0 in HS. I support it just below HS. Okay? So these and these are the same thing. Okay? And alpha 1 is, why do I show you I take this data? Because alpha 1 is very special in the sense that alpha 1 corresponds to the statistical ensemble of these Gibbs measures. And so in dimensions 2 and dimensions 3, these measures are actually really bad because they are supported on distributions, because you get that if you do the calculation for dimensions 2 and 3, then an alpha equals to 1, what you get is that the S in 2D, so this 0 minus and this minus means that I'm just below. H0 would be L2. HS is HS, and the minus means that I'm right below, that I'm rougher than those, and with probability 0, I am in there. So in dimensions 2, you are a little bit worse than L2, and in dimensions 3, you are actually really ugly. You are minus a half minus. Okay? So the measure, even for the heat equation, is actually supported in very, very rough distributions. And this is actually a real problem. Okay? But even in 2D is a problem. Okay. Now, the subject of random data is actually very old. Okay? So it's like people study this in the 20s and the 30s, and goes back to the study of random series on the torus to Paley, Zygmunt, Rademacher, Kolmogorov, Khinchin. And in particular, the Khinchin's inequality, which is very much like the central limit theorem, tells you that you have this square root cancellation that says that if you take the sum of some scalars and you randomly change the signs of these scalars, then the magnitude of this sum is comparable to the square function. That's the same as saying that if you take here p equals to 2, so, and you take these xj's to be randomly plus and minus 1, right? So this is like the Rademacher, could be Bernoulli or whatever, or I mean Rademacher or whatever you want to take. So you take plus minus 1 with probability a half, then the expectation, this is actually almost surely in LP for any p between 1 and infinity. Of course, if p is less than 2, then it's always trivial. But if p is bigger or equal than 2, you're saying that you can control this sum for p bigger than 2 with something that only lives in L2. And this is actually very, very strong. Okay? And this square root cancellation, which, as I said, is the same as saying that if you sum n random variables, then the sum of n random variables is the same as square root of n. It's not n, square root of n. It's the same square root, is this square root gain, right? This is at the core of why problems that have randomization are better or better behaves than problems where you take just any deterministic data. And in order to convince you of that, I want to suggest something that we did in 2019 with Yu Deng and Hei Tian, which is we suggested like a little bit of a paradigm shift that said, look, I mean, people were looking at this random data problem but from the point of view of the deterministic scaling. But deterministic scaling is not the correct lens through which you should view these problems, because the deterministic scaling does not see this square root gain. Okay? And so what we said is actually that there is a different notion of scaling, which we call the probabilistic scaling, which is actually the correct lens through which you should see these random data problems. Okay? And so let's go through this, and I'll show you. I'll go back to the deterministic in a second. So again, we take now very simple data. They're all, this is a single frequency, so I fix n, just a single frequency. And so I have the sum of some random variables, right, at a single frequency. And this is just the normalization n to the minus alpha so that this random variable has unit size in hs. Remember that alpha is s plus the dimension over 2. And then if you look at the linear evolutions of that, the linear evolution doesn't change anything. So that the linear evolution is going to look essentially the same as the data. And so that's also going to have unit size in hs. And let's look now at the second iterate. Okay? So now we solve again as before. We solve the Schrodinger equation for a right-hand side that is it has the linear evolution on the right-hand side, like in Picard iteration. So U2 satisfies simply this equation. And so, look, I mean, if you expect the problem to be locally well posed, in any sense, almost surely, then you expect that the second iterate should remain in the same function space, right? It should not get out. It should also be bounded in HS, right? The function is in HS, the linear evolution is HS, then the second, if you do Picard, you expect the next iterate to stay in the same space. So what does that mean? Well, you fix a time, and let's say we fix k, which is the frequency, n, and we look at the size of the Fourier modes of U2. So bear with me for a second. So this n to the minus p alpha simply came because I have here p functions. That you have this n to the minus alpha, so I have p functions u1. So of course, you're going to have this n to the minus p alpha coming from p functions and this n minus alpha. And then what is it that you have? I mean, you are taking the Fourier transform of a product of p functions, okay, which are sort of like, they have these Gaussian random variables, so those are reflected here. All the k1 through kp, all the p, you have p random variables here. Bar and no bars, because remember, this is complex value. And then you have some set here, which I'm going to call ak, k1, kp, which simply comes from the algebraic relationships that you have when you take the Fourier transform of a product of p functions. What do you get? You get the convolution on the Fourier side, and so you have some algebraic relationships between the frequencies. Okay, and because these are linear evolutions, you also get some relationships between the dispersion relations. You have also this resonant equation. So I'll show you in a minute. So just let's call this AKKP, okay, for a second. I'll tell you in a minute what it is. The point is that if I don't have these Gaussians here, what I'm doing here is simply counting how many points I have in this set. And I'll show you in a minute that the number of points that I have in this set, these are like integers. These are integers in the lattice ZD. All right. So the number of points that I have in this set is actually this number that is in blue. I'll show you where it comes from. But because I have Gaussians here, because these are random variables, you have the square root gain that tells you that actually the size of this is not just the cardinality of this set, but it's the cardinality of this set to the 1/2. And this 1/2 is crucial, because then that says that then if I want U2 to be bounded in HS, that means that I have to multiply this number by n to the s. Oh, sorry, these pointers are like terrible. Okay, you multiply this by n to the s, and then what you want essentially is the exponents to be negative, so all of this is less than 1. And then you are in HS if and only if the s that you have is bigger than -1 over p minus 1. And this is what we call the probabilistic scaling. There's no dimension here. If these were all ones, if you don't have random variables here, if you just take, if all of these are numbers 1, what you get here is you don't get this 1/2 gain. And the number that you get here is exactly the deterministic scaling I showed you before. Now, that deterministic scaling is much larger than this number. So what that means is that you should, when you are taking random data, you should expect to have solutions starting with data which is much more irregular than if you were considering deterministic scalings. Okay? And so let me just tell you quickly where this number comes from. So this number comes from simply, okay, I'm Gosh, that clock goes very fast. Okay, so this number comes from simply counting the following. So you have, this is the set that comes from taking the Fourier transform of the nonlinearity. So essentially, you have to count how many points you have here. The quadratic equation is the resonant equation. K is fixed, and omega is fixed. And so you have K1 through Kp. So if K is fixed and omega is fixed, then if I count K1 through Kp minus 1, Kp is determined. So suppose that K1 is the largest frequency, so you count K2 through Kp minus 1 to the dimension. That gives you this n to the dp minus 2 that is here. And then you are remaining, what remains to count is to count K1. But then the equation of K1 is simply the lattice points that you have on a circle or on a sphere or whatever, which is simply n to the d minus 2 times log n. Okay? And so it's just some basic counting estimates from analytic number theory. So what we are saying here is that this number should be the right threshold through which you should view the random data problems, through which you should say that if you are above this number, I mean, it's a guiding principle because it's not true that you can always reach this number, but it's saying like, well, certainly if you're below this number, things go bad, but if you're above, things go good. And here are some pictures. So this is the same as before. Here the SPR is minus a quarter. So you do the same thing as before, and you see that if you are above this number, things again, you start very, very regular, but things again very quickly become small and smooth. Okay, here look at the scale here, right? But so that's still very good. Okay, it's as good it's as good as the deterministic, but for much rougher data. And if you are below this minus a quarter and you start with rough data, now this is actually zoom out. So this is horrible. You get bad very, very quickly. So things go wild very, very quickly. So there is no way that you can expect a solution. Okay. All right. So this random data problem is just a study of propagation of randomness. And it means that if you start with random initial data distributed according to some canonical law, like Gaussian, in which case you have independent Fourier coefficients, you want to understand how this random structure gets transported when you move along the flow. Okay, so what are the natural questions? Well, what is the optimal threshold or regime where the solution exists and is unique? Okay, at least locally in time. Can you describe the solution? I mean, I just don't want to know whether it exists or not, but I want a description. I want to know exactly how it looks like. If you start with something that is Gaussian, then what happens? How does it look like? And if you have a Gibbs measure associated to your problem, which depends on this alpha that I told you, for alpha 1s you always have a Gibbs measure, then can you justify the invariance and the dynamics, in other words, the existence of global strong solutions in the statistical ensemble of a measure? And so the first person who did a breakthrough on this was Bourgain in 1996 that I show you, who was the first one to go, you see. So in 1996, there was no notion of probabilistic scaling because we brought forward this in 2019. So forget about this for a second. He had a measure that lived below L2. That's what 0 minus is. And the equation he was looking at was the cubic equation in 2D that has deterministic scaling L2, which is what this 0 means. So there is no way that you can find a solution by doing like a fixed point argument, Picard iteration, in just this H0 minus, right? This is super critical. You will never be able to close your estimates. There's no way. So his idea was that said, well, look, I mean, why is this problem bad? This problem is bad is because you start with random data, which is very rough, is below L2. And so let's separate that. Let's separate that from the solution and look at the solution minus this linear evolution of bad or rough data. And let's see what happens with the remainder. And what he was able to show is that actually he could prove by a fixed point argument that the remainder actually lives in HS, which is bigger than 0. So it's smoother. And so his idea was to say, well, I'm going to look for solutions that actually live in this affine ball that is not centered anymore at the origin, it's centered at the linear evolution of the random data. Okay? And this actually was very hard because in order to be able to solve the fixed point argument for the remainder equation, he had to use very, very delicate tools from probability, like these multilinear large deviation estimates, counting estimates, TT star arguments, like these random matrix estimates, and so on. And so what happens below this? Like, I'm telling you that the probabilistic scaling for the cubic equation, even in 2D, is -1/2. And Bourgain was in 0-. So Bourgain could solve the problem when he started in 0-, but actually we are claiming that you should be able to go to -1/2. The problem is that if you start below the support of the Gibbs measure, Bourgain's method fails. And the reason is because if you take random data that is a bit rougher than the Gibbs and proceed with his same ansatz, this V does not regularize. It is not anymore in a regularity above L2, stays below L2. So you can't do anything about it. So how do we solve this problem? By trying to understand where this poor regularity comes from. And this poor regularity comes from, in order to understand that, you have to remember that this V is not a deterministic function, but it's actually a random function. So you need to really put your hands and trying to understand what is the random structure of this remainder. Okay. And so the first question is, okay, where the poor regularity comes from, as I said. And this is the same that happens in the study of singular stochastic heat equation. The poor regularity comes from the interactions of high frequencies in the linear evolution of something rough with low frequencies of the remainder. And so there is nothing you can do about these interactions, these wave interactions. And so in order to be able to do anything better, you need to remove them. So it's not enough to remove the linear evolution of the random data. You need to remove more. Okay? And so the way that we solved this was by, with Yudeng and Haiti and Yue, was through this analog of the theory of regularity structure, but for dispersive PDE. You cannot solve this with regularity structure. It doesn't work, which is what we call the random tensor theory. And what we do here is we sort of unveil the random structure of the remainder and give a very detailed information about the propagation of randomness. And the beauty of this is that this works for any dimension and any number of wave interactions. Okay? It's a unified theory. And so the way that you do this is like, you do it by, you sort of like, by sort of expanding, right? You expand the nonlinearity using the equation itself, and you can do this Feynman type diagrams or trees, whatever, and you get all sorts of trees, which is crazy. Just look at these pictures. And you need to find a way of organizing all of this. And so that's what the random tensors do. What the random tensors do, these are like highly nonlinear objects that actually carry the information of the low frequency components of the solutions. They remain independent with the Gaussians that live at the high frequencies, and they allow us to get a handle of the exploding complexity that arises when you do these high-order iterations or these high-order expansions. And so these are some examples of how the 1-1 tensor or 2-1 tensors will look like. I mean, in some sense, the 1-1 tensor, this carries information of these two here. This is like the solution of low frequencies, okay? This is the linear evolution at high frequencies, and these lines means that I'm inverting Schrodinger on that. So what you see is that what you get here is nothing but a color Gaussian, because we proved that this random tensor, which is just a matrix, is almost diagonal. Okay, and these are examples of 2-1 tensors. Okay, and so what we do is actually we organize this is of high complexity, and we give an ansatz. And so this is the description that I was telling you before. We give this description in which, if we start with data, which is random, I can tell you exactly how this data propagates and how it looks like. It looks like the linear evolution of a Gaussian, a color Gaussian. All these tensors are almost diagonal in the sense that they sort of like localize very much. Sorry, I'm going in the wrong direction. What happened? Oh, sorry. I should finish because All right, so all these tensors are, they carry all the information about the low frequency components of solutions. They're independent with the Gaussians. And somehow the length of how the expansion depends on how close you are to the probabilistic scaling, okay? And in order to prove this, we need to develop sort of an algebraic theory that tells you how you build these tensors from small tensors to big tensors while respecting the dependence between the tensors and the Gaussians within an analytic theory that proves estimates on these tensors and the remainder so that you can sum this expansion, actually. And then the proof goes by induction, and we use the same type of tools that I mentioned before the Bourgain used, plus sort of more sophisticated type of random matrix estimates. And we are able to prove, actually, that this thing converges and that this is the solution. What I want to emphasize here is alpha 1. When alpha is 1, I'm out of time, but I will finish very shortly. When alpha is 1, right, then, and you're in dimensions 2, this is the support of the Gibbs measure, okay, for any power nonlinearity bigger or equal than 3. So put all these terms together into the remainder and only keep the first one. So the first one, actually, is what we call the random averaging operator. And what we did was we say, well, Bourgain only wrote this term plus a remainder. And what we do is we separate one more, which is this one. And then immediately we see that you start below L2. This is in something like h½ minus. And this is actually very regular. It's like h1. So for any power, we are able to actually prove and solve that this problem that was open in 2019, by taking just the first term after the linear evolution, just separating one more term, we were able to prove it, that it works for all n. The same type of ideas together with actually ideas from stochastic PDE and the fact that we knew from the work of Herr that the Gibbs measure was invariant under the heat flow, plus sort of like multilinear dispersive estimates and so on, allow us also to solve this problem. Okay, so in 2022, together with Bjorn Brinkman, we solve actually what is called the hyperbolic phi-4-3 model, which is nothing but the invariance of the 3D Gibbs measure under the flow of the nonlinear wave equation. And so if you look at this picture, the only remaining problem is this one. And let me tell you why two things about why this is a hard problem. Again, because in 3 dimensions, first of all, you are very irregular. The measure is in -1/2. But what gave us hope that we could solve it is the fact that for the wave equation, the scaling is -3/4. So this problem is still probabilistically subcritical, which means that we have a chance. And it's hard because just as with the heat equation, the measure is singular with respect to the Gaussian. So that means that you start with probabilistic dependent Fourier modes, which is very difficult. But we were able to circumvent the things and prove the theorem. And so what remains open is this problem. And let me finish with the challenges. One is to solve this problem. So why the invariance of the Gibbs measures in 3D and the NLS is harder? OK, you have the same problems as before. But the problem is that now, for the Schrödinger, the probabilistic scaling is -1/2, and the measure is at -1/2, which means this problem is probabilistically critical. And what that means is that in the expansion that I showed you before, you gain nothing in each iteration. You never gain. You gain nothing. You gain if you're subcritical, but not if you're critical when you take, say, the interaction of all high frequencies, 3 high frequencies. And the last problem that I want to put forward is what I call the out of equilibrium long-time dynamics, which is the theorem that I showed that gives you a very precise description of how the solution looks like and the random structures of the solution is for short times. And so if you are not in the support of the Gibbs measure, which means that you're in equilibrium, so if you are in the support of the measures, you're in equilibrium. If you get out of the support of the Gibbs measure, even if you're smoother, you're out of equilibrium. Then you want to know how much of this random description survives. Okay? If, for example, it's possible to extend for longer times, the random structure that lies, for example, in the high-frequency components, which is what we had. So many thanks.
operator in your nonlinear situation is like for Feynman cat?
I don't know what Feynman cuts is.
Like, so take some analytic continuation of the Feynman method.
No.
No. Okay.
No. I only use the analogy with the Feynman type diagrams because it's kind of like these trees. You can express them in terms of, it's the same as a finite, but it's not that.
On those lines, you are inverting the...
I'm inverting the Schrodinger operator,
right,
definitely.
So sort of like a propagator in that sense.
It is, yes.
Thank you. You mentioned early on that, of course, besides knowing existence of solutions, we'd like to understand what they look like. Mm-hmm. And even the Gibbs distribution, so, okay, it propagates within that, keeping the distribution invariant, but there must surely be something to say about the evolution beyond just that.
But we do, right? Because what I was saying was that in the case of the 2D, so Bourgain gives you this very easy linear, nonlinear, but what I'm saying is that you could actually say a lot because, sorry, where is this?
So you're saying your expansion really tells you what the dynamics is.
Because actually, let me show you one thing. So, where is it? Oh, I'm going in the wrong direction. I hate this. Here, I'm telling you exactly how it looks like. Mm-hmm. When alpha is 1, okay, all I'm saying is that I could stop after the first one, and that would be enough to prove the measure. But I don't have to stop on the first one. I can continue. Mm-hmm. The same with the problem on the 3D Gibbs on the nonlinear wave. We didn't use this random tensor, we used paracontrol, but we could have used tensor, which gives you much more information about the random structure. It just depends. It depends how much you want to work for the question you want to answer. So, in some sense here, how much regularity you gain as you move from term to term in each iteration depends on how far you are from the scaling. In the Gibbs measure, if in the 2D, for example, that I said that I only kept the 1, I'm at 0 minus, and the measure is minus a half. I'm pretty far, so it's enough to stop above 1. But I could have continued. In other words, I don't need to treat all the remainder as something deterministic. I do it because that's all I need. But I know exactly how it looks.
Okay.
Yeah. For short times. For long times, let me actually be a little bit more careful. For long times, the structure that you get with the first, the second, and the remainder is global. Okay, so when you are on the Gibbs measure, this random structure is global. For short times, we can say more.